Assalamualaikum and greetings to my panels, Madam Arfah binti Ahmad and Prof Madya IR Dr. Gan Chin Kim. Here I would like to present my final year project 2. My name is Nur Farhana binti Mohd Azlan from BEKG S1. My project title is Study of Transformer Condition by Using Machine Learning Approach. For the presentation outline, I will generally give explanation for the introduction, which is a background of the study. Then part 2 is problem statement. Part 3 is objectives to achieve for this study. Part 4, an explanation on DGA. Part 5, justifying the machine learning approach used for this study. Part 6, demonstrating the simulation process and presenting the results. Lastly, part 7 is the conclusion. About the study of research, one of the most important components of the transmission power system is the power transformer. It represents a valuable and expensive piece of high voltage equipment, accounting for up to 60% of the transformer station's overall investments. Presently, most manufacturers claim that power transformers have life expectancy of 25 to 40 years, but this does not take into account the growing demand for improved financial and technical performance, which has pushed power utilities to assess the actual condition of transformers regardless their age. Their dependability has an impact not only on the availability of electric energy in the supplied region, but also on the utilities' cost of operation. Power transformer failures are troublesome for 4 reasons. The first of which is that a transformer failure might result in system operating issues. Large power transformers are typically housed in large tanks containing flammable oil, are hazardous to the environment, and utilities do not have spare in case of maintenance or breakdown. Finally, various types of thermal and electric stresses age the transformer and expose it to incipient faults. In reality, failures of on-load tape changes, windings, and bushings have been reported for power transformers of the all-immersed transformer type. Because of the increased operating pressures, the physical aging of transformers is accelerated by the growth of loads and the expansion of bulk power transactions. It has been difficult to monitor and evaluate the aging square phenomena. The influence of operating circumstances on a transformer varies depending on its manufacture, model, age, and application. Furthermore, if the transformer can live longer than the original manufacturer's typical life estimate, it will be in a good working order and survive for decades. Problem statement. One of the critical elements in the definition of an electrical utilities operation and planning is the health of the transformer asset. As a result, through monitoring systems for power transformers to identify changes in insulation system as early detection, it might be helpful for utility providers to arrange for transformer maintenance or replacement. The DGA method measures the number of different gases dissolved in oil. It is frequently used to evaluate insulation and detect defects such as insulation aging and overheating, oil arcing, and partial discharge damage. Thus, various methods used in inspecting DGA that lead to the usage of machine learning to establish the results from that various assessments. Hence, using 4 different methods, which is Rogers ratio, Donenberg ratio, IEC ratio, and key method to determining the faults and observing on which methods will give the better results. Objective to obtain from the research study. First, to study and investigate the transformer oil insulation faults based on the DGA data. Second, to demonstrate 4 different methods of assessments from DGA dataset. Third, to evaluate the results outcome for the condition of the transformer remnant life. Next is dissolved gas analysis. For many years, dissolved gas analysis DGA has been used as a tool for detecting the types of pending or existing defects within power transformers. The production of specific gases within a transformer has been proved to be a good warning that a breakdown is imminent. DGA of transformers can reveal information on the thermal and electrical stresses that all immersed power transformers are subjected to. DGA methods have grown so precise and efficient in measuring these gases that it has become regular practice for many electric power utility companies as part of routine maintenance. Gas generated from DGA. Fault situations are linked to 8 main gases found in transformer oil. DGA detects the presence of gases that indicate a variety of problems that might result in transformer failure. First hydrogen, second acetylene, third ethylene, fourth ethane, fifth methane, sixth carbon monoxide, seven carbon dioxide, and lastly oxygen. These are 6 different thermal faults in total. First is partial discharge. The corona type can cause deposits of X-wax on paper insulation, or the sparking kind can cause pinholes in paper that tricky to identify. Second is low electric discharge, D1. Large carbonized punctures in paper, carbonization of the paper surfaces, or carbon particles in oil are signs that it occurs in oil and or paper. Third is high energy discharge, D2. Severe destruction and carbonization of paper or metal fusion at discharge extremes, substantial carbonization in oil, and in rare circumstances, tripping of the apparatus indicating a large current follow through. Fourth is temperature below 300 degrees Celsius, T1. Fifth type is temperature between 300 until 700 degrees Celsius, T2. And lastly, 6. Temperature greater than 700 degrees Celsius, T3. For fault severity, a fault in paper is generally considered as more serious than fault in oil because paper is often placed in a high voltage area. For the most severe failures, first, faults D2 in paper and in oil, high energy arcing. Second, faults in T2 or T3 in paper, greater than 300 degrees Celsius. 3. Faults D1 in paper, tracking or arcing. Lastly, faults in T3 in oil, greater than 700 degrees Celsius. For less severe faults, first, fault PD or D1 in oil, sparking. 2. Faults T1 in paper, less than 300 degrees Celsius. 3. Fault T2 in oil, less than 700 degrees Celsius. And lastly, 4. Difficult to find by inspection. Therefore, the DGA dataset was obtained from IEEE Dataport, where that website contains various of standard datasets. Thus, the one that was used in this study project is dissolved gas data in transformer oil fault diagnosis of power transformers with membership degree. In this data, there are completed datasets for all types of faults and key gases of existing gas to determine the fault from transformer. Based on this dataset, it was arranged based on 4 different methods. Next is method of assessments. These are the flowchart for determining DGA fault transformers. However, this study focusing more on this method of assessment DGA. First is Roger ratio method. Roger ratio method is similar to Donenberg ratios, suggests 5 to 6 general fault types via 3 ratios from 5 fault gases. The limitation is ratios generated often yield results not falling into any of their suggested fault types. Next, IEC ratio method. For fault analysis, the IEC 605993 ratio technique is frequently employed. For diagnostic analysis, the technique uses ratio for specific gases. The technique relies on a mix of ratios, gas concentrations, and gas growth rates. In order to identify incipient failures, 3 gas ratios are employed. Next is Donenberg ratio method. Donenberg ratio method suggests 3 general fault types based on the calculation of 4 ratio based on 5 key gases. The limitation is ratio generated often yields results not falling into any of the 3 suggested fault types. Lastly, key gas method. For key gas method, considered as modification of the TDCG procedure, permit tentative determination of possible fault types empirically determined from a transformer's unique gas profile. Focuses on which gas is the largest portion of TDCG, useful for benchmarking in the normal range and to confirm diagnosis in the warning range. The limitation is high tendency to return inconclusive results. If a severe fault occurs and involves the paper insulation, all gases will be high yet insufficient to register a fault if using the specified values according to the standard. Next is machine learning approach. In this research, the machine learning approach that utilized to perform the simulation on finding transformer health is SOM or Self-Organizing Map Machine Learning. What is SOM? SOM is the Self-Organizing Feature Map. is a clustering approach for no teaching supervision and guiding. The network's architecture is made up of one input layer and two output layers. The number of nodes in the input layer of the sample's input dimension, where each node represents an input sample of a component of the input signal received by input neurons. Why using SOM? There are lots of researches related on determining the condition of transformer health, and DGA have different methods of assessment to achieve the fault outcome results. The number of groups produced for the study of evaluations is one of the most helpful characteristics of these artificial neural networks. Self-organizing maps are different from other artificial neural networks in that they utilize competitive learning rather than an error correction learning, like backpropagation with linear regression, and they use a neighborhood function to maintain the input space topological features. So SOMs may be used to visualize low-dimensional views of high-dimensional data similar to how multidimensional scaling works. Next is the simulation process and results.
First of all, open MATLAB software, then import data that have been arranged in different methods into the workplace so data can be selected from this workplace later. After that, at the command window, type NC2 to generate the neural network clustering app and continue next. At the input data, at the drop-down menu, select the method of input data that wants to be clustered and select matrix row so that it detects for 3 or 4 gases ratio as input with 30 samples data. At define a self-organizing map size section, type 10 showing 10 size of 2 dimensional so the output for the size of topology is 100 outputs, then next. Click on Train to train the network using batch SOM algorithm. Note that training multiple times will generate different results due to different initial conditions and sampling, hence the outcome of the analysis still quite the same. For SOM topology and SOM neighbor connections, the size and outputs map are the same for each 4 methods since the topology of SOM layer and connections have the same 100 size outputs. Then, by clicking on different plots to figure out the mapping outcome for different ratio method.
For the first method is Roger ratio method. From the visualization map of ratio analysis, first map showing majority of yellow connections indicate that it is highly connected. At the bottom left, some red connections showing the different input and weight connection. For SOM input planes correlate with SOM sample hits, the third input planes showing a similar weight. For fault analysis, in SOM input planes, input for fault T2 and T3 shows a similar map. Conclude that the faults that observed from Roger ratio is local to severe overheating. For IEC ratio method. For IEC ratio analysis, SOM input planes show similarity from input 1 and input 2. Based on the SOM sample hits, the weight are more on the right side of the map. From fault analysis, SOM input planes shows the result of input 1 and input 5 correlates with the weight on the SOM neighborhood weight distance. It can be seen on SOM sample hits, the weight are more prominent on upper right, which concludes the fault's outcome are quite unclear to observe. Next, for the Donenberg ratio method. On Donenberg ratio method, the analysis from gases ratio, input 2 and input 3 show similarity in terms of colors that indicate the faults are clearer on sparking that cause to local overheating. As the fault analysis, input 3 and input 5 have similar outcomes with the ratio analysis before. In conclusion, for Donenberg ratio method, the results are showing that the transformer is having sparking that lead to overheating. Lastly, for key gas method ratio analysis, since the method using the original data of key gases, the outcome that can be observed from the visualization map is undefined. The same goes for fault analysis. Input planes show similarity for each of the method that gives the conclusion ambiguous. Result discussion. SOM neural network clustering app will generate the outcome in terms of visualization map, which is easier to see and analyze the results. Different colors will indicate different meaning and showing whether the links of neurons connection are weak or strong. from the visualization map also can evaluate the weight of neurons based on where the clustering is more prominent, and by correlating all the topology from one method can determine the outcome. However, to make a sturdy analysis on the overall fault, adding an analysis based on the fault analysis, which is arranging the gases ratio data referred to their fault type. Therefore, from the visualization map, can observe what type of fault is more similar to the gases ratio analysis. Furthermore, for the overall study research on the transformer health based on the DGA data, the outcome results are catered to the predicted results from the previous research on final year project 1. Hence, by analyzing overall different method of assessment, it can be concluded that Rogers ratio has given quite convincing result rather than other methods. However, Dornenberg ratio method shows a result of high energy discharge that leads to overheating temperature between 300 and 70 degrees Celsius. For IEC ratio and key gas methods, the results have similarity with each other that caused the results were unclear and obscure. To give more clearer observation on visualization map results, here is the table shown for each of the methods with the results. Lastly, for conclusion part, as a result, it was discovered that techniques that read particular codes with specific codes are more accurate when making predictions. This is because they are more exact in their interpretation of data into the code for each situation. When the data does not match the existing codes, however, these algorithms are unable to make prediction. As a result, they have a lower level of consistency in identifying the defect and are less accurate when predicting the whole case. The IEC ratio and key gas methods are affected since both methods does not have specific code and the outcome was unclear. Thank you for your time and attention.